Normally we see relations as equations and not sets of the connections. The reason why is because equations depict how relations actually relate to numbers, and they encode infinite ordered pairs. You don't need a list of them out. You can just use the equation, and that will give you all of your ordered pairs. Now, equations will normally be continuous, not discrete, when they're using an equation to describe it. This is graphed. The previous relations that we've seen have been graphed as points, but these kind of relations will be graphed as curves or lines. Any kind of line that you draw is going to be a continuous relation. And really, you need to use a graphing software whenever you're trying to draw these things out. There's never a reason to draw by hand unless you're really strapped for time or you don't have a computer near you. But if you do have to draw by hand, then a table of values gives you a good place to start. So when you create a table of values to find, what you're trying to do is trying to find like 5 to 7 points, and you're using the table of values to find those points. The more you can do, the better it is, but 5 to 7 is a good starting point. And you always want to choose values of x that make the equation easy to solve, because you have to do this a bunch of times. Might as well make it as easy on yourself as possible. And what the table of values really shines is that solid lines on graphs are just infinitely many points connected. There's so many of them on the graph that you just draw them as a solid line instead of each point. And like you're not going to draw a point like this. No, you're just going to draw a solid line like that. And that covers all those points. Okay, let's look at this in practice. We have this equation, this relation here, y equals 3 minus x squared. And we're going to create a table of values. So I have my x values, my y equals 3 minus x squared, and then my y values as a result. And I want to choose these 5 values because they're close to the origin, and they're really all I need to show the behavior of this graph. Why are these the only ones I need? Well, I know what this graph looks like. I know how these graphs work, and so I know this is all I need to show it. If you don't know those things, you need to just test a bunch of values or just graph it on a graphing software. Okay, so that's going to give us y equals 3 minus negative 2 squared, y equals 3 minus negative 1 squared, and so on and so forth. Okay, and now for the y value, all we have to do is calculate these things out. Well, 3 minus negative 2 squared, that's going to be 3 minus 4, that's negative 1. 3 minus negative 1 squared is 1, so that's going to be 2. 3 minus 0, so 3. 3 minus 1, 2. And 3 minus 4, negative 1. Okay, and these are the 5 points I've just found. Of course, using the table of values, you can see that the first point I get is negative 2, negative 1. And then I get negative 1, 2, then 0, 3, just using the x value and then the y value to create the ordered pair, and 2, negative 1. And all I've done here is just graph these, right? Negative 2, negative 1 is right here. Negative 1, 2 is here. 0, 3, 1, 2, 2, negative 1. And that was a lot of work for something that could have been done quite simply by just plugging in the relation into the graphing software and plotting it. And of course, it hits every single one of the lines because it's the same thing. Okay, let's do another one for y equals the absolute value of x. So this one, same idea. I'm just going to create a table of values just to show you how it's done. There's really no reason for you to do this, but just to kind of show you the process. Once again, I'm going to use these 5 values. I don't need these 5. I actually really only need these 3, negative 1 to 1. But let's just go ahead and do it. And the absolute value of negative 2 is 2. Absolute value of negative 1, 1, 0, 1, 2. So we get negative 2, 2, negative 1, 1, 0, 0, 1, 1, and 2, 2. I don't need to graph this, or graph these points. I'm just going to graph the line. And this is the absolute value of x. 0, 0 is right here, of course. There, the origin. 1, 1, sorry, that's 2, 2, which is the last point. 1, 1 is just down here. I can get on there. There it is. Negative 1, negative 1, or sorry, negative 1, 1 is there. And then finally, negative 2, 2 is right there. So they're all on the graph already. Use graphing software whenever you can. Desmos.com is a fantastic one to use. It's free to use and it's powerful. So give it a try in numbers 5 and 6. Okay, we can use the graphs to analyze some important features, some key features such as the domain and range, as we talked about before, and intercepts. So for the domain, that we're asking what interval on the x-axis is the graph above or below. So the domain is always tied to the x-axis, the horizontal one, the independent one. And so you're looking for when is the function above or below the x-axis, and that is your domain interval. The range will be parts of the y-axis, and you look at what part of the y-axis is the graph to the left or right. And these things will typically be intervals of the real number line. So we're going to use interval notation to describe the domain and range. So for this first one here, I've actually created this little graph that has these movable points. And all I'm doing here is I'm just going to draw where the graph comes down to the x-axis. And this x-axis is going to be our domain. Of course, it starts right here, right? It doesn't go anything over here. It starts at this point right here. We zoom in on it a little bit. And it ends at this point here. Now you can also see that there we have an a closed dot on this side of the function, right? That's a filled in dot right there. And on this side, we have an open dot. That means it's going to be evaluated at this point, but not at this point. It goes all the way up to this point, but not at it. So if this is the ending spot here, this ending spot happens at 4, and this ending spot on this side happens at -6, the domain of this first function is going to be -6, including it, so a bracket, up to 4, but not including 4. Okay, likewise, we can do the same thing for the range. The range, we're just looking at everything to the left or right, and we're looking at the y-axis here. So the lowest value is going to be this value down here at -2. You can see it does hit -2 because it's a solid line all the way down there. And the highest value is, of course, 5. Again, a solid line, so we know it hits 5 there. And everything in between is covered by this green bars. So you can see that everything is hit between those two values. So the range is going to be from -2 up to 5. And of course, since this is an interval, the real numbers, you always start with the lowest value first, then the highest. That means you always start left to right when talking about the domain, and you always start bottom to top when talking about the range. Okay, same idea here for this function, or for this relation, I should say. This relation starts here. Just kind of imagine your mind it flattening down to the x-axis. This is the first value it hits on the x-axis. This one is going to be at 2, right? and it goes up to this value here, 5, but it does not hit 5. It just goes up to 5. So that means we go from -2, sorry, that's -2, up to 5. -2 is included. 5 is not. The range value, well, that's going to be from this lowest value here, right? It flattens down to the range. That's going to be -6. We're going to include -6 because it's a solid dot. All the way up to, that's going to be what, 6, 7, 8. But it does not hit 8. Now, real quick, I just want to show you a different style of graph using this thing here. I'm going to turn off these and show you an infinite one. So this graph continues indefinitely to the left, and it continues to the right like this. It just keeps going downwards. So the range, or sorry, the domain value is the blue, right? I can just keep dragging this thing all the way over this way. I can just keep dragging it. And to the right side, if I just drag this out, you can see wherever it shows up, that's where the domain is. And you can see it's still showing up. It's still showing up. It's still showing up. Even though it looks like it doesn't hit there, if I zoom out far enough, it does actually hit that spot. And I can keep pulling it out. All of this stuff is covered in the domain. So actually, it just keeps going on to the left and to the right indefinitely. That means the domain for this relation is -infinity to infinity. It's the entire real number line. The range, you can see that the highest value there is at 10. And I can just keep drawing it downward as much as I want. It'll keep hitting the function on this side. So the lowest value in this case is -infinity. Always start with the lowest value. It just keeps going on downwards. So that means it hits -infinity. And the highest value is right here at a peak at 10. And we're going to include 10 because it's a solid line there. There's no open dot shown on this graph. So, all right. Now, we've talked about domain and range, but we have not talked about intersections. And if a graph crosses the x-axis, the point of intersection is called the x-intercept. The y-coordinate at the x-intercept, well, if it crosses the x-axis there, then that means the y-coordinate at this point must be 0. Because on the x-axis, all of the y values for every ordered pair that's on the x-axis, all the y values are 0. If the graph crosses the y-axis, this point of intersection is called the y-intercept. Just imagine the Cartesian coordinate system, right? If we're on the y-axis, so some relation looks like this. No matter where you cross on the y-axis, all of the x-coordinates are going to be 0 because they're crossing at the y-axis. So you don't go left or right at all. You just stay there on the origin. Then you go up or down. So the y-intercept has x-coordinates of 0, and vice versa. The x-intercept has y-coordinates of 0. Y-coordinate, of course, refers to the y portion. This is the y-coordinate. And the x-coordinate just refers to the x portion of the ordered pair. Okay, so for all these three relations, we're going to ask what's the domain, range, and intercepts. So I've got three relations here. And what are the domain, range, and intercepts? Well, normally, if you're going to see a static image, if it continues off the edge, that means it continues indefinitely. Here on Desmos, we can just pull it, and you can see it continues indefinitely that way, and it continues indefinitely this way as well. So This is the full relation here. You can see that it continues definitely to the left and to the right. I can keep going out to the left and zooming out. I can still find the function, so it just continues indefinitely this way. Likewise, it does the same thing to the right. It continues indefinitely that way. So we know that the domain for this first function is negative infinity to infinity. The range, likewise, I can keep going upward, right? It just keeps going up and up and up and up. So all this stuff is included in the range. The same thing is true downward. I can just keep going down. All of this stuff is going to be included in the range. So the range is also negative infinity to infinity. Okay, the x-intercept, that's where it crosses the x-axis. Well, that is, I'm looking at here, it looks like it's like it looks like it's 0.6. I can just click on the graph and Desmos will actually find it for us. That is at 0.6. So the x-intercept is at 0.60. In fact, since this coordinate will always be 0, all you really need to say for the x-intercept is the x-coordinate, 0.6. Because we know the y-coordinate has to be 0. And looking at this graph, the y-intercept, you can see, well, it's definitely at 1. So likewise, if I said the y-intercept is at 0, 1, I could just say the y-intercept is 1 because the x-coordinate of the y-intercept has to be 0. Okay, looking at this next relation, you can see it's just a circle. The domain is all the values that it runs through. The first value is at 1. Last one's at 5. So the domain is 1 to 5. And the range, the lowest value is at 2. The highest at 6. And the intercepts, where does this relation cross the x and y axes? Well, it doesn't. It doesn't cross the x-axis at all, and it doesn't cross the y. So all we gotta say is none. Okay, finally we have this relation here. It's just a flat line. It goes indefinitely to the left and to the right. So we know the domain must be everything. The range, however, is a flat line. That means the only value it ever hits is right here. And that value is at -4. This is not an interval. This is a single point. So we're going to use a set notation to do that. The range is just -4. It hits no other y values. You can go ahead and like click on the line and drag it out. You can see it's always -4 on the y coordinate. You can go as far out as you want. It'll always be -4. Okay, x-intercept, well, this line never crosses the x-axis. It's actually parallel to the x-axis, and it'll never go up or down, so it will never cross it. So there's no x-intercept. We do, however, have a y-intercept. That's just at -4. So the y-intercept is -4. You can, of course, say 0, -4, but there's no need. -4 does everything we need to. Okay. For this relation here, we're going to find the intercepts algebraically. We're not worrying about the domain range right now. We will find that, but we're going to find the intercepts algebraically, and then we're going to look at them and see if they are accurate on the graph. So to find the intercepts algebraically, right, for the x-intercept, the key thing to note is that y equals 0. So if I plug 0 in for y, we get 0 equals -4x plus 3. And this is just a linear equation. So I can solve it by subtracting 3 to both sides. I get -4x equals -3. Then divided by -4. And we get x equals 3/4. So our x-intercept is at 3/4 or 0.75. our y-intercept is when x equals 0. So we have y equals negative 4x, negative 4 times 0 plus 3. This is just an expression that we need to evaluate. Negative 4 times 0 is 0, plus 3 is 3. So the y-intercept is at 3. Graphing this relation, we get y equals negative 4x plus 3. I think that's right. Negative 4x plus 3. And we can see that the x-intercept is at 0.75, which is the same thing as we found. The y-intercept is at 3. So we've done that correctly. And the domain and range of this thing, well, it does in fact keep going over. If I zoom out far enough, it will always hit all of these values. I just gotta zoom out far enough. The same thing is true for this way. I just need to zoom out far enough, and you can see it just keeps going indefinitely this way. So it goes indefinitely to the left and to the right. It also goes indefinitely down and up. So our domain is negative infinity to infinity, and our range is the same. Okay, the intercepts of this graph, the domain and range as well. So the intercepts is where it crosses the x-axis. That's what we're going to look at first. So the x-intercept. This one actually has two x-intercepts. We have one right here, and that looks to be at, let's see, this is going to be 0.5, so it's going to be negative 1, negative 2, negative 3, and positive 3. So the x-intercept is going to be at negative 3 and positive 3. The y-intercepts, again, there's two of them. We have one right here at positive 1, and one down here at negative 1. So positive and negative 1. Of course, we can just click on the graph, and Desmos actually labels the intercepts for us, negative 3 and 3, 1 and negative 1. So we've got it correct. Now, the domain of this thing, of course, the furthest value to the left is negative 3. The furthest to the right is 3. And everything in between is covered by all of this stuff here. So the domain is going to be from negative 3 to 3, including both endpoints. The range, likewise, the lowest value is negative 1, and the highest value is 1. And it does hit everything between, right? It does go all the way down in between that. So all of this stuff is covered, to the left or to the right. So we're going to include both the endpoints, and that is the range. Okay, give it a try in number 7. Okay, does negative 1, negative 9 satisfy the equation 5x plus 8y equals 9? Well, to do this algebraically, all we have to do is plug in, negative 1 for x and negative 9 for y, and see what we get. 5 times negative 1 is negative 5 minus 72. That's, of course, negative 77 equals 9. This is a false statement. And that should tell you, well, that probably means that the point does not satisfy the equation. So it's not a point in the relation. What point does satisfy the equation? Well, you can calculate it, right? We can just plug in a value for x. So if we plug in, for instance, x equal to 1, then all we have to do is type in 5 times 1 plus 8 times y equals 9, and then calculate it. So this is going to be 5 plus 8y equals 9. Subtract 5. We get 8y equals 4. Y equals 1/2. So the point 1/1/2 satisfies this relation. Let's go ahead and graph it and see what we get. 5x plus 8y equals 9. And this is the relation right here. Let me plot the point that did not satisfy, -1, -9. -1, -9. And that, you can see, is not even close to the line at all. It's way off of it. That's the reason why it didn't work when we plugged it in. However, the point 1, 1/2 is right there. So 1, 1/2 does satisfy the line because it's on the line, the equation. And so other points to satisfy it, well, just drag the line. All of these points satisfy the equation. So any one of these things, there's of course infinitely many of them. This is a continuous relation. There's just so many points to choose from. Okay, give number 8 a try.